For decades, scientists have been chasing a ghost, a cosmic architect they call dark matter. And just recently, a quiet breakthrough powered by technology straight out of a sci-fi novel might not only have caught this ghost but fundamentally changed the rules of the game. This isn't just a discovery about the universe. It's a powerful lesson about persistence, innovation, and uncovering the hidden forces that shape our lives. Let's paint the picture. Our universe is a vast, intricate tapestry. For centuries, we thought we understood its threads. The fiery birth of stars, the majestic spin of galaxies, the cosmic dance of gravity pulling it all together. We looked out with our telescopes, listened with our radio dishes, and built a beautiful model of reality based on the matter we could see and interact with. The protons, neutrons, electrons that make up every atom in your body, in your coffee mug, in distant nebulae. This is normal matter, and for a long time, we thought it was everything. But then, the universe started whispering secrets that didn't fit our perfect picture. Astronomers noticed that galaxies were spinning too fast. Stars on the outer edges, which should have been flung into the void like stones from a rapidly spinning sling, were clinging on tight. Clusters of galaxies, enormous cosmic cities, were held together by a gravitational force far stronger than all their visible stars and gas could possibly account for. It was like watching a carousel spinning at breakneck speed, but seeing the riders staying perfectly still without holding on. Something invisible was providing the extra grip. That something became known as dark matter, and the more we studied the universe, the more we realized it wasn't a minor anomaly. It was the main event. Scientific estimates, refined over decades of observing cosmic background radiation, galaxy formation, and the bending of light, gravitational lensing, tell us a staggering truth. Normal matter, the stuff of you and me and everything you see, makes up a mere 5% of the universe's total mass and energy. Just 5%. Think about that for a second. Everything we've built our understanding of the cosmos on, every star we've named, every planet we've explored, every element on the periodic table, it's just a footnote in the universe's true inventory. So what makes up the rest? About 70% is a mysterious force called dark energy, which is pushing the universe apart at an accelerating rate. And the remaining 25%? That's our elusive giant dark matter. It's 5 times more abundant than all the stars and galaxies combined. It's the invisible scaffolding upon which the cosmic web of galaxies is built. It's the gravitational backbone that holds galaxies together, shaping their elegant spiral arms and dictating their movements through space. Without dark matter's silent gravitational hand, galaxies might never have formed in the first place, and the universe would be a much emptier, less interesting place. Yet, despite its overwhelming influence, dark matter has remained utterly invisible. It doesn't emit light, absorb light, or reflect light. It doesn't seem to interact with normal matter through the electromagnetic force, which governs light and chemistry, or the strong and weak nuclear forces, which govern atomic interactions. Its only detectable interaction, it seemed, was through gravity. For decades, physicists have been on a relentless hunt for the particles that make up dark matter. They theorized candidates like WIMPs, weakly interacting massive particles. Particles that would be massive but interact so rarely with normal matter that they would pass right through solid objects like ghosts through walls. The search became a global scientific quest of epic proportions. Scientists built massive detectors deep underground, shielded by miles of rock to filter out cosmic rays that might mimic a dark matter signal. They cooled these detectors to temperatures just fractions of a degree above absolute zero, hoping to catch the faint energy left behind if a dark matter particle did happen to bump into an atom in their ultra-pure target material. They sent sophisticated instruments into space, looking for indirect signs like the faint gamma rays that might be produced if dark matter particles collided. and annihilated each other in the crowded centers of galaxies. Billions of dollars were spent. Thousands of brilliant minds dedicated their careers. Countless hours of painstaking work were poured into building these complex experiments, collecting data, and analyzing results. And year after year, decade after decade, the answer came back. The same. Nothing. A persistent, frustrating, deafening silence. The ghost remained elusive. Doesn't that struggle resonate with you on a deeply human level? This relentless pursuit of something crucial, something you know is real and influential, but which remains just out of reach. Think about your own life. Maybe it's that dream you've been chasing for years, a creative project, a business idea, a personal goal that feels like your cosmic purpose. You pour in the effort, work late nights, sacrifice leisure time, and still, success or completion feels like a particle that just won't interact with your detector. You put in the hours, you follow the conventional wisdom, you do all the right things, but the breakthrough, the moment of connection, the tangible result, just doesn't appear. It feels like hitting a wall, like shouting into the void. Perhaps it's been a personal challenge, overcoming a fear, breaking a stubborn habit, finding clarity on a difficult life decision. You try the standard approaches, read the self-help books, get advice, but the core issue, the dark matter of your internal landscape, seems resistant to all your efforts. You feel its influence, the way it shapes your actions and reactions, but you can't seem to get a direct handle on it, to make it interact in a way that brings resolution. Or maybe it's even bigger, a search for answers to life's profound questions. Meaning, purpose, connection. You look for external signs, follow established paths, seek guidance, but the deepest truths, the invisible forces that give life its richness and depth, feel frustratingly intangible, just beyond your grasp. The decades-long hunt for dark matter, with its escalating efforts and repeated disappointments, mirrors these personal struggles. It teaches us a profound lesson. Sometimes when the conventional methods fail, when applying more force or more time to the same problem yields diminishing returns, the answer isn't in working harder within the existing framework. It's in questioning the framework itself. It's in realizing that maybe, just maybe, you're trying to catch a ghost with a net designed for fish. It's in acknowledging that the truth you're seeking might require a completely different way of looking, a paradigm shift in your approach. For the scientists chasing dark matter, that different thinking didn't come from bigger, colder, or deeper detectors. It came from a place few would have expected to hold the key to the universe's most baffling mystery, the realm of quantum computing. Enter the stage, the unexpected hero of our story, Intel's quantum computing system. Now, when you think of high-energy physics experiments or massive detectors, you picture enormous machines, often buried miles underground, requiring vast amounts of energy and infrastructure. You picture something colossal, complex, imposing. Intel's breakthrough looks nothing like that. The core of their system, the quantum processor doing the heavy lifting, is a marvel of miniaturization, no bigger than a fingernail. Let that sink in. The potential key to unlocking a quarter of the universe's composition fits on your fingertip. Contrast this with the traditional approach, building cathedral-sized detectors like the Super Kamiokande in Japan or the LZ experiment in South Dakota. These required extreme environments, temperatures near absolute zero, colder than the deepest space. Miles of solid rock overhead to shield from the constant bombardment of cosmic rays, and megawatts of power to run sophisticated electronics and cryogenic systems. They were designed like impenetrable fortresses, waiting in silent, frigid isolation for that one incredibly rare ping that might signal a dark matter particle had, against all odds, bumped into an atom. It was, as the article puts it so vividly, like trying to hear a whisper in the middle of a hurricane. You build the most sensitive microphone possible. You put it in the quietest place imaginable. And you listen with every fiber of your being, knowing most of what you hear will just be the residual storm. Intel's quantum system operates on an entirely different principle. First, and incredibly, it works at room temperature, or at least at temperatures far, far warmer and more accessible than cryogenic detectors. It uses significantly less power, less than a desk lamp, compared to the electricity needs of a small town required by some traditional labs. This isn't just an engineering feat. It's a philosophical shift in the search. But the real game changer is how it looks for dark matter. It doesn't wait for those vanishingly rare direct collisions. Instead, it leverages the bizarre, interconnected nature of quantum mechanics. Imagine the universe as a vast, interconnected quantum field, constantly humming with subtle energies. Dark matter particles, even if they rarely bump into normal matter, are still part of this field. They move through it, they influence it, and in doing so, they create tiny, subtle ripples, disturbances in the quantum fabric itself. Intel's system is designed not as a collision detector, but as an incredibly sensitive quantum field sensor. It's like spotting footprints in the sand without ever needing to see or interact directly with the person who made them. The quantum processor acts like a master listener, not waiting for the loud bang of a collision, but attuned to the faint shh of dark matter passing by and disturbing the field. This breakthrough is more than just a technological leap. It's a profound testament to human ingenuity and the power of thinking differently. We see this principle play out in our own lives all the time, often on a smaller scale. Think about a problem you faced that seemed insurmountable using your usual methods. Maybe your car made a strange noise, and your first instinct was to take it to the expensive mechanic. But instead, you decided to approach it differently. You searched online forums, watched a YouTube tutorial, and discovered a simple fix you could do yourself, saving time and money. You didn't apply more traditional effort, working longer, hours at a job to afford the mechanic. You applied a different kind of thinking, leveraging collective online knowledge, learning a new skill. Perhaps you were trying to stick to a budget, and your old method of just hoping you didn't overspend wasn't working. Instead of just trying harder to say no, you tried a different approach. You used a budgeting app to track every expense, or you started batch cooking meals on the weekend to reduce impulse buys. You didn't just apply more willpower, you changed the system, the method of attack. Intel's quantum leap reminds us that true innovation often comes from daring to break free from established conventions. For decades, the convention in dark matter hunting was bigger, deeper, colder. Intel dared to go smaller, more accessible, and quantum. By leveraging the mind-bending principles of quantum mechanics, like quantum entanglement, where particles become linked and share information instantaneously, no matter the distance, and superposition, where particles can exist in multiple states at once, their system created something truly novel. It didn't just look for a particle. It created a quantum net, a detection field woven from the interconnectedness of the quantum realm, capable of spotting disturbances millions of times more subtly than traditional methods. And this fundamentally different approach yielded a result that billions of dollars in conventional experiments couldn't achieve. It detected the signatures of weakly interacting massive particles, WIMPs, the very candidates physicists have been chasing fruitlessly since the 1980s. After all that searching in the expected places, the answer came from an unexpected angle, using unconventional tools. But here's where the story takes a turn from exciting discovery to mind-bending revelation. Intel's system didn't just detect WIMPs, it observed how they interacted, and what they saw was utterly unexpected. Scientists had theorized that WIMPs, living up to their name, would interact weakly. They'd pass through normal matter almost, completely unaffected, leaving only that faint, occasional trace energy if they happened to make a direct hit. They were expected to be like passive ghosts, just existing and exerting gravity. Instead, the particles Intel's system detected seemed to do something far more active. They temporarily altered the quantum states of the particles within the quantum sensor. This wasn't just a passive passing through. It was a subtle, fleeting interaction at the quantum level. Imagine the universe as a perfectly tuned orchestra. Scientists expected dark matter to be like a massive, silent audience member, just sitting there, their weight influencing the acoustics of the hall, gravity. But what they observed was more like an audience member who, as they moved, subtly shifted the pitch of some of the instruments for a fraction of a second. This observation suggests something profound. Dark matter particles might not be just inert, massive blobs exerting gravity. They might possess quantum properties of their own. They might be interacting with the quantum fields of normal matter in ways we never anticipated. This is like discovering that the invisible architect of the universe isn't just laying the bricks and mortar, gravity, but is actively shaping the blueprints, quantum interactions, in real time as the building goes up. The implications are staggering. If dark matter has its own quantum properties and interactions, it could explain why galaxies form with the specific structures they have, why the cosmic web looks the way it does. It's not just passive gravitational scaffolding. It could be an actively organizing force at the most fundamental level. This discovery doesn't just identify a particle. It challenges the very foundation of modern physics, the Standard Model of particle physics. The Standard Model has been incredibly successful at describing the fundamental particles we know and the forces that govern them, except gravity. But it doesn't include dark matter, and it certainly didn't predict dark matter would have these kinds of quantum interactions. This finding is a clear signal that the Standard Model, as complete as we thought it was, is likely only part of the picture. Doesn't this idea of realizing that your fundamental understanding was incomplete hit home? Imagine spending years, maybe even your whole life, operating under a certain set of rules or beliefs, only to have a sudden revelation that changes everything. Perhaps you grew up believing that success meant following a specific path, getting a certain degree, landing a prestigious job, accumulating wealth and status. You chased that vision relentlessly, only to reach it and feel empty. Then, perhaps unexpectedly, you discovered fulfillment in a completely different area, a creative passion, a quiet life of service, building strong relationships. The rules you thought governed happiness or success were only half the story, or perhaps not your story at all. Your personal Standard Model needed an update. This quantum breakthrough is that kind of wake-up call for the entire field of physics. It doesn't just add a new chapter, it suggests the need for a whole new volume. It forces scientists to grapple with the possibility of a quantum Standard Model, a new framework that could potentially unify quantum mechanics, the rules of the very small, and general relativity, Einstein's theory of gravity, the rules of the very large. For a century, these two pillars of physics have remained stubbornly separate, describing reality beautifully in their respective domains, but clashing when applied together. Bridging this gap has been the holy grail of physics since Einstein's time. This discovery hints that dark matter, through its quantum nature, might be the key, the missing link between the quantum world and the gravitational universe. It's a powerful reminder, both in science and in life, that growth often comes not from having all the answers up front, but from embracing the unexpected, the things that don't fit neatly into our existing boxes, and being willing to redraw the map. So how exactly did Intel manage this feat? What's the technical magic behind this quantum net? It centers around their specialized quantum processor. This chip isn't like the silicon processors in your laptop or phone. It uses superconducting circuits that exhibit quantum properties when cooled to extremely low temperatures, though still much warmer than traditional dark matter detectors required. The processor contains 128 qubits, the quantum equivalent of classical bits. But unlike bits, which are either 0 or 1, Qubits can exist in a superposition, a combination of both 0 and 1 simultaneously. They can also be entangled, their fates linked regardless of distance. These properties are the source of quantum computing's potential power and its sensitivity to the subtle quantum world. These 128 qubits are arranged in a specialized lattice pattern, designed to maintain their delicate quantum state, their coherence, for as long as possible. Coherence is crucial because it's when the qubits are in their quantum state that they can perform complex calculations, or in this case, act as ultra-sensitive sensors. Intel achieved a coherence time of an astonishing 9.7 milliseconds. Now, 9.7 milliseconds might sound like the blink of an eye, and it is in human terms. But in the quantum world where interactions happen on timescales far, far shorter, 9.7 milliseconds is an eternity. It's long enough to run complex algorithms, long enough for the quantum net to be cast and maintained. These algorithms are the invisible brains of the operation. Evolved from advanced concepts in quantum field theory, they instruct the qubits on how to set up the detection field, how to leverage superposition and entanglement to create that hypersensitive state. Instead of waiting for a particle to physically collide with an atom and deposit energy, the system uses the quantum state of the qubits themselves as the sensor. When a dark matter particle passes by, even without a direct collision, its gravitational or potential quantum influence subtly perturbs the surrounding quantum fields. The Intel system is designed to detect these minute perturbations, these tiny ripples in the quantum fabric, by observing the resulting changes in the qubit's superpositions, states. This approach creates a detection field millions of times more sensitive to these subtle interactions than traditional methods which rely on direct, energetic collisions. It's like swapping a single tripwire designed to be tripped by a heavy object for an invisible web of threads that quiver at the slightest breeze. And remember the power consumption? Less than a desk lamp. This technology is a masterclass in efficiency, leveraging the unique properties of the quantum world to achieve extraordinary results with minimal brute force. This focus on achieving maximum impact with minimal resources is another powerful lesson applicable to our daily lives. How often do we assume that solving a problem requires more money, more time, more effort, more complicated tools? Think about streamlining your daily routine. You might not buy a new expensive gadget. Instead, you might reorganize your kitchen pantry for efficiency, or plan your outfit the night before, or batch cook meals on Sunday to save time and energy during the week. You're not adding more resources. You're optimizing the ones you have, applying smart planning and a different perspective. Or consider managing your personal finances. You don't necessarily need a bigger paycheck to improve your situation. You might download a budgeting app, meticulously track where your money goes, identify unnecessary expenses, and redirect those resources. You're not adding more income. You're applying a smarter strategy to your existing flow. Intel's quantum system exemplifies this principle. The biggest breakthroughs don't always require the biggest machines or the most raw power. They often require the smartest ideas, the most elegant designs, and the willingness to explore unconventional approaches. It's about doing more with less, leveraging inherent properties like quantum mechanics, rather than just applying brute force. It's a reminder that resourcefulness, ingenuity, and a willingness to think outside the box can be more powerful than sheer scale. The implications of this dark matter detection go far beyond simply confirming the existence of a particle. It opens the door to an entirely new way of observing the universe. Because this quantum system can detect dark matter's presence and subtle interactions rather than just waiting for rare collisions, it could potentially be used to map where dark matter is distributed throughout the cosmos. Intel isn't stopping at the lab. They are already collaborating with NASA to explore developing satellite-based quantum sensors. Imagine sensors orbiting the Earth or venturing deeper into space, quietly listening for the quantum whispers of dark matter, mapping its presence across vast cosmic distances. For the first time, we might be able to truly see the universe's invisible skeleton, not just inferring its presence from gravity, but directly sensing its distribution. We could map the intricate filamentary structure of the cosmic web, the vast network of dark matter that spans the universe, connecting galaxies like pearls on invisible threads. We could see how dark matter clumps and flows, how it shapes the large-scale structure of the cosmos. This could revolutionize our understanding of cosmic history. For example, it could rewrite our theories about the Big Bang and the early universe. Scientists currently believe that tiny fluctuations in the early universe, amplified by gravity, eventually led to the clumping of matter that formed stars and galaxies. Dark matter's gravity played a crucial role in pulling this normal matter together. But if dark matter has its own quantum properties and interactions, perhaps it wasn't just a passive gravitational anchor. Perhaps dark matter played a far more active role in the universe's initial moments, influencing its structure and evolution in ways we never imagined. Mapping its ancient distribution could reveal the fingerprints of the universe's earliest organizing forces. This idea of mapping the invisible, of finally seeing the hidden structures that shape reality, hits home in our everyday lives too, doesn't it? How often do we overlook the hidden forces, the unseen scaffolding that supports and influences our own journey? Think about the quiet support of a friend or family member who consistently lifts you up, often without fanfare. You see their visible actions, but you might not fully appreciate the invisible structure of love, loyalty, and encouragement they provide. The dark matter of your personal universe. Consider the small, consistent habits that build success. Over time, the daily 5 minutes of meditation that grounds you, the regular exercise that maintains your health, the commitment to reading a few pages every night that expands your knowledge. These aren't always dramatic, visible acts, but they are the invisible structures that hold together your well-being and progress. Intel's quest to map dark matter reminds us to look deeper in our own lives, to appreciate the unseen forces, the subtle structures, the quiet support systems that shape who we are and where we go. By acknowledging and valuing these hidden influences, we can see our own world with fresh eyes, recognizing the complex web of relationships, habits, and beliefs that truly hold our lives together. The potential of this quantum sensing technology stretches far, far beyond the cosmos. The ability to detect incredibly subtle interactions at the quantum level with minimal power and in more accessible conditions has transformative potential right here on Earth. Intel is already exploring adapting its quantum sensing technology for medical applications. Imagine medical scanners so sensitive they could detect the earliest quantum-level changes in cells, potentially identifying diseases like cancer long before any symptoms appear, or traditional scans can find them. Early detection is often the key to successful treatment, and this technology could revolutionize diagnostics. Consider geological applications. Quantum sensors could potentially detect minute stress changes deep within the Earth's crust at the quantum level, offering the possibility of predicting earthquakes with greater accuracy than ever before. This could save countless lives and prevent immense destruction. Think about environmental monitoring, detecting pollutants at incredibly low concentrations, or materials science, understanding the quantum properties of new materials for revolutionary technologies. This is the true power of fundamental breakthroughs and of thinking small to solve big problems. A tiny quantum chip, born from the abstract pursuit of understanding the universe's biggest mystery, holds the potential to address some of humanity's most pressing challenges, from health and safety to environmental protection. These potential applications should inspire us to reflect on our own potential and the power of small actions. We often feel overwhelmed by big problems, whether in the world or in our own lives. But this story shows that monumental change can stem from unexpected places and subtle beginnings. What small change could you make today that might have a massive rippling impact tomorrow or a year from now? Maybe it's deciding to learn a new skill for just 15 minutes a day. Maybe it's reaching out to a mentor or someone whose path you admire. Maybe it's simply taking a moment each day to practice gratitude or mindfulness, shifting your internal state. These actions might seem small, almost imperceptible, like a faint ripple in a quantum field. But like Intel's tiny sensor detecting dark matter's subtle influence, these small, consistent efforts can build into profound transformations, shaping your future in ways you can't fully predict. Intel's quantum breakthrough shows us that even the most abstract curiosity can lead to practical applications that improve lives, and that the smallest, smartest actions can ripple outwards, changing the world around us, starting with our own. Of course, a discovery this significant, one that potentially upends decades of searching and challenges fundamental physics, doesn't just appear overnight and get universally accepted without scrutiny. The scientific world, while buzzing with excitement, is also approaching this with healthy skepticism and rigorous verification in mind. The findings have reportedly passed initial peer review, the critical gauntlet where other experts in the field pore over the methods and results, and are slated for publication in a prestigious journal like Nature Quantum Physics. A major milestone. Now the real work begins. Independent verification. Major physics laboratories around the globe, institutions like CERN in Europe, Fermilab in the United States, Kamioka in Japan, and others, are undoubtedly gearing up. They'll be analyzing the details of Intel's method, attempting to replicate the results, and designing their own experiments to either confirm this quantum detection or find alternative explanations. This crucial step ensures that this isn't a fluke, a misinterpretation, or a subtle error. It's the bedrock of the scientific process: peer review and replication. The lead researcher mentioned in the article, Dr. James Thomson from MIT's Quantum Information Center, reportedly called it a paradigm shift in both computing and cosmology. That kind of language from a leading expert underscores the potential significance. And it's worth noting that the sophisticated quantum algorithms behind this breakthrough didn't appear out of thin air. They evolved from years of theoretical advancements in quantum field theory, built upon the work of countless physicists before them. This is how science progresses, not usually in isolated flashes of genius, but through the slow, collective building of knowledge, where one team's theoretical work enables another team's experimental triumph. This moment in scientific history reminds us powerfully of the essential role of community and collaboration. No single person, no single lab could have achieved this alone. It required theorists developing the quantum field concepts, engineers building the complex quantum hardware, computer scientists writing the advanced algorithms, and physicists interpreting the results within the vast context of cosmology. It was a collective triumph, built on decades of shared knowledge, published research, and collaborative efforts across institutions and even continents. We see this same principle in our own lives. No one truly succeeds alone. Whether it's the encouragement of a mentor who sees potential you don't, the support of a family during a tough time, the collaborative energy of a team project at work, or even the shared learning within an online community. We thrive when we lean on others. We build upon each other's strengths, fill in each other's gaps, and celebrate each other's successes. The dark matter discovery isn't just Intel's story, it's the story of physics as a global community working together towards a shared, monumental goal. It shows that our biggest leaps are often the result of standing on the shoulders of giants, sharing our own insights, and working side by side. So, if this discovery holds up under verification, what's truly next? The most thrilling possibility is that this detection of dark matter's quantum interactions could be the first tangible clue towards bridging the biggest gap in modern physics: the chasm between quantum mechanics, the rules of the tiny world, and general relativity, the rules of gravity and the big world. By revealing dark matter's quantum nature, Intel's system might provide the thread that connects these two currently incompatible descriptions of reality, potentially leading us towards the unified theory Einstein spent his later years dreaming of: a single, elegant framework that explains everything. Such a theory wouldn't just be a philosophical victory. It could unlock unimaginable possibilities. Understanding gravity at the quantum level might lead to insights into phenomena we can only speculate about now. Could it reveal new, currently unknown particles? Could it provide a path towards harnessing new energy sources or developing technologies that currently belong in science fiction? It could even reshape our understanding of fundamental concepts like the nature of space-time and the very fabric of reality. Think about the last time you connected two seemingly unrelated ideas or skills in your own life, and it sparked something new and powerful. Maybe a hobby you loved unexpectedly gave you a unique perspective that revolutionized your approach to your professional work. Maybe a casual conversation with someone outside your usual circle opened your mind to a new way of seeing a problem. This potential unification of physics is that kind of connection on a cosmic scale, bringing together two vast, seemingly separate domains to reveal a deeper, more complete truth. It challenges us to look for the links, the hidden connections, in our own lives and ideas, because that's often where the most profound transformations begin. What can we, living our everyday lives far from quantum labs and cosmic voids, truly take from this incredible saga? The pursuit of dark matter, for all its frustration, teaches us the power of persistence, the necessity of curiosity, and the courage to embrace the unknown. It shows us that the most important truths might reside not in the obvious places, but in the shadows, waiting patiently for us to develop the right tools and the right perspective. Intel's quantum breakthrough demonstrates that innovation often comes from breaking the rules, from questioning conventions, from daring to think fundamentally differently. Whether it's rethinking the search for a cosmic particle or reimagining our own career path, our relationships, or our approach to personal challenges, stepping off the well-worn path can lead to astonishing discoveries. And perhaps most importantly, this story reminds us that life, much like the universe, is full of invisible forces shaping our journey. Sometimes we're so focused on the visible, the loud, the obvious, the job title, the bank account, the surface-level interaction, that we miss the subtle, underlying currents. The quiet strength of character being built through hardship, the invisible bonds of love and support, the subtle shifts in perspective that happen internally. The key sometimes is to stop chasing the obvious with conventional tools and start listening for the subtle ripples, the faint whispers of what's truly influential and real beneath the surface. So, I want to leave you with this thought. What is the unseen force guiding your life right now that you haven't fully acknowledged or understood? Is it a dream you've shelved? A fear you haven't faced? A quiet strength you've yet to tap into? Or maybe a subtle limiting belief that's been holding you back? Take a moment, right now, to reflect. What small step could you take today? What different perspective could you adopt to begin uncovering your own dark matter? Let this cosmic story inspire you to think differently about your own challenges, to trust in the power of persistent curiosity, and to believe that even the smallest, smartest actions, like detecting a faint quantum ripple, can ripple outward and change everything. This journey into the quantum universe and the quest for dark matter is far from over. If this discovery holds up, it's truly just the beginning of a new era in physics and technology. What do you think this breakthrough means for our future? Could it really unlock the secrets of the universe? Or is it just the first step into an even deeper mystery? Share your thoughts in the comments below. I'd absolutely love to hear your perspective and discuss it with you. And if this quantum leap into the unknown blew your mind as much as it did mine, and you want to keep exploring the cutting edge of science and discovery with me, please hit that subscribe button and turn on notifications. We dive into fascinating topics like this every week, and you won't want to miss what's next.